Let's imagine a clean data set where there's no missing data, no duplicate records, and definitely no corruption. You're imagining a unicorn. Data sets like that only exist in fiction. In this talk, I'm going to talk about how we implemented the PSIG algorithm for finding duplicates at scale using Apache Spark. I'm Huon Wilson. I'm a senior software engineer at CSIRO's Data61, working on the Stellar Graph analytics team. We've been working on PSIG and entity resolution and other graph-related algorithms. So first, I'm going to make sure we're all on the same page and using the same terminology. I'll talk about what is entity resolution. Then, I'll talk about the PSIG algorithm. And finally, for those familiar with Apache Spark, I'll talk about what we learned when implementing it using Apache Spark. So, first things first. Maybe you haven't heard of entity resolution. What is it? Entity resolution is matching records. So we might have two data sets, which each represent different attributes about certain entities, like people or businesses. And we want to merge those two data sets into one unified one, where we've got a single record for each of those entities that combines the attributes from those two data sets. Or we might have a single large data set where we have dirty or corrupted duplicate records. And these duplicate records need to be either deleted or we need to create a new data set where we've merged those duplicates. Ironically, given entity resolution is talking about duplicates, there's many different names for it. Maybe you've heard of deduplication or record linkage. I've put 6 names here, but this paper mentions 17 different ones. Throughout this talk, I'm going to talk about a specific example data set. So I've made up 5 people, 5 records, I should say, where there's a name, an address, and a phone number. In the best case, our data sets would have some sort of unique identifier, like a driver's license number for people, or a business number for businesses. But that's too much to hope for, usually. So for this one, there's no such thing. We have 3 different people here. A human could probably guess that we have Min Tran twice and Mary Taylor twice. But all of these records are slightly different. For example, there's missing data. There's records that are just completely missing a field, as well as missing components within a field. So we're missing a suburb here. There's also typos or corruptions. So Min Tran has lost the diacritics on her A, and this suburb has been misspelled. And, of course, there's abbreviations and initialisms. So Mary Taylor has become M. Taylor, Road has become RD, and some of the phone numbers don't list the country code. Entity resolution is taking these 5 records and resolving them down to the 3 people that they represent. If we have some way to score or test whether 2 records were the same people, we'd be able to do a naive approach. So we could take the first record, compare it with all the other ones. Our scoring function might give us a number between 0 and 1, say the Jacquard similarity using the record within the data. I've just made up some hypothetical scores here. But you can see that we've sort of associated a score for the similarity with that first record to all of the other 4. Next, we compare the next record with the 3 after it. This is a nice optimization because we don't have to compare with the first one. We've already compared with it. And so on and so forth. We compare each record with the ones later. For these 5 records, this is pretty easy. It's only 10 comparisons. Not too bad. However, as the title of the slide suggests, this naive approach scales quadratically. For 100 records, we have to do 5,000 comparisons. For 1 million records, we have to do 500 billion comparisons. This is not scalable. So we've seen what entity resolution is and why it might be hard. Now, what is this PSIG algorithm I keep mentioning? It's a way of dividing up our data so that we don't get a quadratic explosion in the number of comparisons that we have to do. So the first step is we start with our original data, unsurprising. And then we compute a series of small sets of records called microblocks. Within those blocks, we link up the data. And we hope that those links will only be between records that might be the same entity and not between records that are probably different entities or obviously different entities. Once we've created these links, we can then score or verify them to create a graph, a network of our records and then the links between them with weights for the scores. This entity resolution algorithm was created and published by, just let me check my notes, the Australian Transactions Reports and Analysis Centre, or AUSTRAC as a more reasonable way to say it, which is an Australian government agency that works with money laundering and other illegal financial transactions. The name PSIG comes from this paper, where they call it probabilistic signatures, PSIG. How does microblocking work? Well, we have a series of candidate signatures, which we generate from the data. Each of those candidate signatures is like a scattergun attempt to hash or summarize some identifying information out of the data set. So for this, each of those signatures has to be chosen per data set. And for this one, maybe we've chosen to use the initials plus words from the address. So for Mary Taylor here, we get MT66 as one candidate signature, and we get MT Egerston as another one, and so on for each of the words in the address. It's typically good to use multiple candidate signatures because it is a scattergun approach. And so we might also pair the last name with words from the address. This gives us Taylor 66 and Taylor Egerston, and so on. We do this for all of the records. So for Michael Taylor, we'll get MT66 again, and Taylor 66 also again, but we'll get different information like MT Hayfield. Once we've done this for every record, we create a reverse index, or the set of records that generate each candidate signature. So for MT66, we see that records 1, 2, 3, and 5 were the ones that correspond to it, the initials plus the words from the address. For other signatures, it will be different. So for MT Egerston, we have 2 and 5. Once we've created all of these reverse indices, we can then put them into a table where we have the candidate signature on one column and the IDs in another column. The sets of IDs, I should say, in another column. This is the key step that will connect records to try and find the true entities. And hopefully, when two records correspond to the same true entity, like the 2 for Min Tran, they will exist in the same block. However, I'm sure you could guess that there's going to be some of these candidate signatures that are really common. There's probably going to be a lot of people who live in New South Wales with the last name Smith. So Smith, New South Wales, as a candidate signature, is going to have potentially millions of records. PSIG models this uninformative nature of some signatures by putting an upper bound on the size of the sets. That upper bound has to be chosen on a per dataset basis, but typically small values work well. Maybe we've done some data science to determine that 4 is a good upper bound, and so we eliminate sets that are of size 4 or larger, in this case, MT66. If you're familiar with other entity resolution techniques, you might notice that this differs to so-called standard blocking because standard blocking only has one block per record, whereas PSIG allows a record to be in multiple blocks. All of these blocks here have 2 and 5 in them. Those standard blocking techniques are forced to use fewer, larger blocks because they need to optimize for recall, whereas PSIG can optimize for precision and have many small blocks. And then, because we can put a record into multiple blocks, this helps raise our recall. Remember how we had to do 10 comparisons before? Now we only need to do 3 by just comparing the records within each block. So we can compare 2 and 3, 2 and 5, and then 3 and 5. We don't have to do the duplicate comparisons for the records that are paired in multiple blocks. Going from 10 to 3 is a huge saving, and on bigger data sets it will be an even bigger saving. Finally, let's suppose we've used the phone number to do some additional blocking that's linked the 2 records for min-tran. So we've now got a larger set of potential of candidate signatures and the associated sets, and then we can put that all into a graph. When we do the comparisons along the links, we can associate the score to that link. So for the previous side where we had the 3 comparisons, we've got this top set of 3 records where we've got Mary Taylor twice and Michael Taylor, and then the scores associated with them. Once we've got this graph, we can then process it into our set of true entities. And so one simple but effective approach is to choose some threshold for the score, delete the edges that are lower scoring, and then compute the connected components. So again, the threshold is something that has to be chosen per data set. And maybe we've done data science to work out that 0.5 is a good threshold. So we delete the lower scoring edges, and we're left with 3 connected components. We've got one for Mary Taylor, one for Michael Taylor, and one for min-tran. We've now correctly identified our 3 people out of our 5 records, and depending on what we want to do for our data set, we can either merge them into single records or delete the duplicates. That's the PSIG algorithm. It will use candidate signatures to compute a series of potential micro blocks and then score within them to create a linked record graph which we can process into our entities. Now, for those who are familiar with Spark, we used it to implement PSIG, and what did we learn? For large data sets, obviously, processing on a single machine can take a long time, so using a cluster can be beneficial. And on the Stellar Graph team, we've been using Spark for a variety of graph analytics and deep learning tasks. We use Spark for PSIG as well to try and integrate with those. The first thing that's been said before, and should be said again, is that data frames are usually better than resilient distributed data sets, or RDDs. This is true for PSIG as well. We first implemented PSIG using RDDs, which is the old Spark form for representing data. And then we migrated to data frames. When we did that migration, we recorded some benchmarks. So we've got the first row, we had 10 million records in our synthetic data set. The PSIG with data frames ran 4 times faster than the PSIG with RDDs. Next, we tried with 50 million records on our moderate-sized cluster. And we found that the RDD code was still running after 8 hours. We got bored and killed it. Meanwhile, the data frame code took only 6.5 minutes. So, as far as we know, it's at least 70 times faster. Why might that be the case? Well, RDDs are a distributed list of self-contained individual Java objects, whereas data frames are a distributed table of data columns. These are quite similar to like a distributed version of a pandas data frame or an R data frame. This table representation gives Spark much more insight into how the data is stored and much more control over it. This lets it be more compact, which means lower memory usage and less garbage collector overhead. And that's really important when you're getting close to the memory limits of your cluster. Additionally, Spark data frames come with the so-called Catalyst query optimizer. This query optimizer is very similar to an SQL query optimizer in a conventional database like Postgres. And it will take sort of a bird's eye view of your whole computational pipeline and transform it to run more efficiently. After doing that optimization, it will even then generate specialized Java code for that particular query. That specialized Java code can then be like compiled and jittered by the JVM as per normal. However, when we were doing the transition, we were iterating fast with small data frames. So we had 10,000 records, and we're just running on my laptop in local mode, obviously on a single machine. The default settings meant the data frame RDDs ran in 17 seconds, pretty short. But data frames in their default settings took 80 seconds. That's more than 4 times slower. What's going on? The explanation is that the number of partitions for data frames defaults to 200. So data frames are being split across 200 little segments. This is a lot of overhead. Spark typically recommends using about 3 times the number of cores, so that's 3 times 12 for my laptop, 36, much smaller than 200. Data frames default to a more reasonable 12. It's not perfect, but it's smaller and means less overhead. However, even when we fixed that using the appropriate Spark default parallelism and Spark SQL shuffles partitions, Spark configurations, to make it match RDDs, so we used 12 for both of them, the data frame code took 20 seconds. Still slower than the RDDs. What's going on? Well, what's going on is the optimizer is like a big fixed overhead, and it's using a non-trivial amount of time. But to confirm this, let's look at a profile. So a profile is like a recording of your code as it runs, and you can get insight into the performance. In this case, we represent our profile as a flame graph. And a flame graph represents the call stack of your functions from bottom to top. So you got main on the bottom, and then everything it calls going up. And the x-axis, the width, is proportional to the amount of resources it uses. In this case, that's CPU time. And so on the left, we've got a lot of green, red, and blue code. That's Java and Scala code, and that's our Spark application. That's our useful execution time. And so that takes up about half the screen. So that's using about half of our CPU time of this run with 10,000 records and 12 partitions. On the right, we've got a lot of yellow code. That's C++, and that typically means that it's within the JVM, the Java virtual machine itself. How do we create this? We used the async profiler project. We tried to look for a Spark profiler that would work on a cluster, but we couldn't find one. So we sort of just ran a normal JVM sampling profiler, which can generate flame graphs like this. We'd love to extend it to somehow run on a cluster, but that's like much more work than just using it in its normal settings. Let's zoom in and confirm our suspicion. By looking at that yellow section, we see compile, compile, compiler, compile, compile, compile. All of these are referring to the C2 JVM compiler. So that's a just-in-time compiler that will convert from Java bytecode into optimized machine code to make our code run even faster. This is suggesting that compilation maybe does have something to do with why our 10,000 record case is slow. In fact, it's taking about 40% of the total CPU time. If we compare that to a bigger data set, say 1 million records, using exactly the same program, with exactly the same settings, just more data, we find that that yellow section has shrunk dramatically. It's gone down to just 15% of the total execution time, suggesting that compilation, that Catalyst query dynamically generating Java code, and then that Java code being optimized by the JVM, that process is just a fixed overhead that will disappear in our larger data sets. This is confirmed by our comparison earlier, where we had 10 million and 50 million records. Of course, profiling is really useful outside of Spark and the JVM, and flame graphs are as well. Next, we had to think about partitioning, and specifically how the data is partitioned, not just the number of partitions. So when we're doing that scoring step, we need to use information from both ends of each link. So we have to compare Mary Taylor with the M. Taylor record. Before we can do this, we need to make sure that they're on a single executor machine. You can't just compare things you don't know about. And that requires a shuffle in some form. Shuffling data across the network can be very expensive. If we could use some sort of better partitioning strategy, where we got these connected components all within a single machine automatically, we wouldn't have to do as much shuffling and our code can run faster. We got a 10% speed up by using a 2D edge partition strategy, which is a probabilistic approach that restricts where a link can go, and so increases the chances that the data will be on the right machine. So we saw some things we learned when implementing psig with Spark. Now, let's finish up. In summary, we saw that entity resolution is matching or deduplicating records, and it can be hard to do naively. Next, we saw that the psig algorithm will take our original data, compute microblocks, and then score within the links, score within those blocks to create a linked record graph. And it does this in a way that hopefully avoids the quadratic overhead explosion in the number of comparisons. Finally, with Spark, we saw that data frames were good, that profiling was really helpful in diagnosing a performance problem, and that partitioning makes our code run faster. psig doesn't solve entity resolution. There's always more work that can be done. We'd love to make psig work on live data streams, where instead of having to, when you get new data, instead of having to recompute with the whole data set, you can just recompute with the new data or some much smaller set of data. Next, remember how we used a very naive strategy of just thresholding and then looking at connected components to work out our entities? Maybe we could do something better about clustering or something for the linked record graph. Finally, or thirdly, our candidate signatures are very manual, and we have to think about them for each data set. It'd be great if we could somehow use deep learning to choose our candidate signatures, choose our thresholds, and generally do the whole process. Now finally, if we had a graph data set where our records are linked to each other, maybe we could use that extra information about a neighborhood of a record to somehow improve our entity resolution. Graphs are particularly interesting to me and my team because we're working on a scalable network graph analytics platform. We've got an open source library on GitHub, and we're hiring for a senior software engineer, as well as other roles. We've got a booth here, and you can visit stellargraph.io/careers. As a second part of my pitch, two of my colleagues are speaking as well. Kevin's speaking about an application of graph machine learning to Bitcoin tomorrow at 10:50 in this room, and Pantelis is speaking about using that open source Python library to do graph machine learning and comparing two algorithms. He's also in this room tomorrow at 3:40. Thank you.